Hello, welcome to this lecture, a continuation of our previous topic, which is the Module 8, the 2-point boundary value problems. So, in the previous video, we discussed the concept or the theory behind the 2-point value problems. And in this module, we discuss about the finite difference method, and we have observed from the previous video how to solve a very simple second order differential equation. And if you have a system, if you have a model, you can actually solve for n order differential equation, meaning if you can still go to 1000 order differential equation if you have a robot, for example, so, or a building, or if you have a very complicated system, the greater the number of order. Okay, you might think of this as the degrees of freedom. So meaning if you have a complicated circuit systems models, so you will have more order, so the simplest for the 2-point boundary value problem, the simplest system that we can solve for now is the second order differential equation. And we've learned the finite difference method and how to derive these things. Now, if you have more order here, like more than 2 or nth order ODE, so for nth order nth order ODE, so you will have y to the n, right? So, and then you will have this expression here. Now actually this one can be expressed from the previous n minus 1, and then from the previous y prime. Okay, so y double prime is y I minus 1 minus 2yi plus. So this is actually, if you can remember, this one is simply the y prime minus y prime divided by 2h, right? So, and then you have y prime is equal to y minus y over yeah, I think here you have 2h. So we have solved that this one is similar to this one, h squared. So we have proved last time that this one should be 2 or something, that we can derive, okay, this one here we can derive actually to this case, no? So for the nth order you can have the same expression, like for example here this is actually y n minus 1 minus y n minus 1, but this one is I, and I minus 1 divided by 2h. Okay, so then here you have y n minus 2 minus y n minus 2, then you have I and I minus 1 divided by 2h. So but the same idea, you have a graph, and then you have the curve, and then you have the boundary. Say this is A to B. Okay, so your system is bounded in this certain curve. So your goal is to get the area between, so you get the integration, for example. And yeah, we have discussed this one in the previous module. So now our goal for today is to do a concrete problem solving example. Okay, so we have here a second order DE differential equation with linear boundary value problem. Okay, so then the m is equal to 10, and we know that m is the number of slabs, or the number of your panel, no? So in this curve, for example, we divide this one to 10, then we get the approximation of that one, no? Okay, so and then so the curve can be represented by okay, individual panel. So the summation of individual panel will result to the curve, no? So representation of the curve. And then given the boundary conditions, y of 0 and then y prime pi of 2. You might wonder how come this one is in the first order and then this one is in the second. Actually, because of this expression, okay, you can construct the from the given solution. Okay, so we have the expression here the last time. Okay, can the previous example here, if you can remember, can recall, you can move this one. I'm sorry, I think we need to remove. Uh, so, okay, so we go back to this equation. Okay, this is actually from the previous one here. You might observe, no, this is the same. And from this, I can move a bit higher and sorry, then zoom a bit. Okay, so you can see that our given the boundary is here, and then the other one is y prime. So you have this one. So therefore, we have this equation here, and then equation here. So then, since we have alpha already, and then we have the beta, so the number of variables is equal to the number of equations, and then we can solve the problem. Okay, so this is a system of linear equations, and you can observe here, okay, from this example, you have we have the analytical solution, no? Y equals x minus sine 2x. So this solution, this is solved analytically. Actually, if you replace y prime, okay, y prime equals negative 4y plus 4x. If you replace y with x minus sine x, sine 2x, then take the second terms of x and then negative 4y plus, y becomes so y becomes x minus sine 2x and then plus 4x. Okay, and if you derive this one two times, so you have 0 minus 2x cosine something, and then again this becomes positive, but this one becomes 4 sine 2x. Okay, if you derive this sine 2x twice, then that become 4 sine 2x. Now it also becomes positive. And then also, if we forgot to put a negative 4. Okay, so this becomes negative 4x plus 4 sine 2x. Okay, sorry, I think you okay, just okay, I think now it's clear. Then plus 4x. So we just cancel out the 4x, and then you see that 4 sine 2x is equal to 4 sine 2x. Okay, so this is the analytical solution, and you can solve using I think in this case you can solve using variable separable method, no, in differential equation. Okay, and also yeah, but it is not our concern here to solve the analytical solution. Our goal is to solve this using different numerical methods. Okay, so using this equation in the above. So okay, we solve this one. using the following variables, using the following user-defined equations. So you have, we will use the LU decomp and then the LU solve tree. Now, if you can remember this in module number 3, if I'm not mistaken, module 3 or 2, 2 or 3, this one is the same as LU decomposition, but this is intended for symmetric problems, no? So because here we will have a symmetry, no? We will have a symmetry. And then LU, these are LU decompositions in module 2 or 3. Then we have the equations. You see that this is, our equation is expressed in DCEB. Actually, if you, okay, so you can actually, we can remove this one here. Okay, I think it's okay, so we can replace that one. Actually, we can form a simultaneous equation, no? Meaning from these three equations, this one, and this one, you can create a matrix, no, wherein you have the y0, y1 up to ym. Okay, if you arrange the equation, and then all here is the other side will be the coefficients, or let's say for example here the alpha, y0, so this is 1, okay, and then the rest is 0, okay, because there's no other, for y1 there's no y1 in this equation, so the rest is 0, but the alpha is 0 also, so therefore here 0. So that's the first equation. Okay, and before we proceed to the second, we proceed to the last, no, and see what is the expression, or maybe the second. We can see the second here, the second equation at I is equal to 1. Okay, so you have I is equal to 1, y0. Okay, so here you can write y, okay, so that you don't confuse yourself. You have here y0, then minus 2y1 plus y2, okay, minus h squared times x1. Now the function here comes from the equation, this one here, the one, the function is actually this one here is y prime, right? So this is y prime is equal to negative 4y plus 4x. So therefore this is negative 4y1, because this is xi, so this yi, so this is 1, then plus 4x1, okay, equals to 0. So therefore if you arrange this one, all the x on the right hand side, so you look at the x1 multiplied by h squared, so that's negative 4h squared x1, so transpose becomes positive, that becomes h squared, or 4, sorry, I forgot to write the 4h squared x1. Okay, so you can write the x1. Okay, and then the rest, you have the y0, so you have y0, the first, this is the y0, this is 1 because there's one y0 here, and then the y1, so you have two terms, this one here and then this one here, so you just add the two, so you have okay, so this is not the same as the other one here, so this is another term, so this one is equal to negative 4h squared, and actually positive, no, that's positive. We can start from here, negative 2y1 plus 4h squared. Now actually we don't write the y there because it's already on the other side, so plus 4h squared. Okay, and that's y1. So if you multiply the two matrix, this already with y1, no, but you don't, so that's the expression, and then so on and so forth. Y2, we forgot the y2. This is 1 here, so meaning you have 0 here, then 0. Okay, and then here becomes 0, then this becomes 1, and then actually you just continue at I is equal to 2 at y2, so this becomes negative 2 plus 4h squared, and then 1, and then 0, and then so on. Okay, until the last here, the last expression, you substitute the given, which is y prime pi over 2 is equal to 0. Okay, now actually the x here, um, yeah, sorry, y prime, b at b, so you have beta is equal to 0. Okay, so at x is equal to pi over 2, y is equal to 0, and then sorry, y prime is equal to, at x is equal to 0, y is equal to 0 based on the given boundary. So this one is based on the y of 0 equals 0. Then y prime of pi over 2 is uh, equals to 0. Okay, so this is here 0, and then 1 for the y minus 1. So but I just want you to see the difference. Actually this is the same, which is the beta becomes 0. So let's replace this one with another. Let's replace this one with yellow. Okay, so this becomes 0. We can cancel that one, and then the same term with the middle matrix, so that's actually negative 2 plus 4h squared, and then the ym is negative 2. Okay, so negative 2, yeah, that's the last term. This is aligned to this one. Okay, aligned, and then this is the second m minus 1. So this is a m by m matrix, and then this is 1 by m by 1 matrix, and then this one here is m by 1 matrix. Okay, so you see the expression here. So this is a simultaneous. Okay, so replace x1 with, for example, here you replace x with this one, and then you have the value of y prime. Okay, and then also for here, I think this is also 4h squared x m. Okay, so and then the rest here the same value for h squared x. Okay, the same. So you have simultaneous equations. Okay, you have simultaneous equations. So okay, so I hope you it's not just simply to understand this one and from the previous module, and then we proceed with we express this matrix. Okay, we express this matrix into a code. If you notice here, actually this one here is the expression of all the diagonal. Okay, the one in the diagonal, which is negative 2 plus 4h squared. So h2 is h times h, so that's h squared. So this is the d, except that the first one is 1. Okay, so you notice the first in the diagonal is 1, so that's the 1 here. And then this one c is the one in the right hand side, left hand side, and actually this is 2. This is 2. If we go back to the to the expression here. So this is actually 2 compared here, which is only 1. So this is actually 2. Sorry, get that. So that's the only term on that diagonal. That's only 2. And then, okay, the rest is 0. And then here, on the right side of the main diagonal, 0, 1, 1, 1, 1, 1. So you have um, the first, this is the B. Sorry, not B. E. This is the E. E of 0 is 0. Okay? And then the B is expressed in the X matrix. Okay? So if you notice, you have the X and then 4H squared. Okay? But the only difference is that the first term is 0, which is correct, no? Here, 0. So this equation will be used in the LU decomposition. Now, since this is a symmetric, okay, symmetric equation, meaning you have almost all that equation similar, and the rest are, we can call it the sparse matrix, sparse matrix, meaning there are many there are many zeros in our matrix, so therefore we use the LU decomp tree. Okay, so that's it. So that's your equation. The equations are matrix form, and when we get the, so our goal is to get the y, no, y. But this time is the y should be expressed in numerical values. Okay, so start from 0 to a certain pi over 2. Okay, based on the boundary x here from x 0 to x to pi over 2. So that's our range. So x at the left and then x at the right. Then you have the mesh spaces. So 10, and then you have the h, which is the distance between the two. If we try to draw the graph, we have here from 0 to pi. Let's say, assuming that's the curve, this is from pi over to 0, so that's the range. And then the panel will be divided by 10, no? So there are 10 spaces, and then h is between this one. This will be your h, and all the h, okay, all the intervals are equal or identical. So this is the formula. Okay, so and then we arrange or the just simply a notation, no, for the idea for the, sorry, for the intervals. And then we write the equations based on the x. Okay, our x here is from 0 to pi over 2. Actually 0 pi over 2 divided by 10. So pi over 2 divided by 10 times 2, something like that. So there are 10, no? So 0 value here, let's say x1, then x2 until x 0, 10, and then 11, yeah, 11, and 2h. So actually the h here is equal, stop, yeah, so the interval is, yeah, that's the idea. So that's the x, and then the h is one value, and then you have the m, which is 10. So we solved the equation. Okay, so we solved the simultaneous equation. So if you haven't gone through the numerical methods on solving the simultaneous equations, this one, so it would be better if you go back to that module number 2 or module number 3. I think that will be module number 2. So the LU decomposition. So as long as our number of variables is equal to the number of equations, meaning the number of y here is equal to the number of equations. Okay, so and then we print the result. Here we have the m is equal to 10, and if you notice our if we substitute our um, at here at the pi at x, okay, so go, okay, at x is equal to pi over 2, sorry, is it pi over 2? Yeah, at pi over 2, the y numerical value is 1.56418, but so our result is 1.56481, but the one in the numerical, I can call it exact, is equal to 1.570796. Okay, so this exact is that exact is comes from this equation. Okay, using other way of solving it, no, analytically, but our answer here is this one, 1.56. If you ask me which one is exact, of course the one in the analytical solution. Okay, but the computers cannot solve it, no, cannot do analytical solutions. So now this is our result, and the error is somehow about 0.42%. Well, it's not that bad, but depends on what kind of problem, okay, and what kind of at what kind of system. Perhaps you need a smaller error value, so you need to increase the number of m, or the panel, no. So instead of 10, you make it very thin, no. So when we increase the m is equal to 10, sorry, 100, so using the same steps, you will get, okay, at x is equal to 1.57, sorry, yeah, our result is 1.57073, which is, okay, which is very close to the actual result. Okay, so the error is less than 0.01%. So, well, this one is accurate. Okay, you can call it accurate. So depends on the significant digit. So depending on your problem, no, if the problem will ask you for error value less than 0.0001, so you need to increase the value of your m. Okay, so that's our first problem solving um, in the, yeah, using the second order differential equation. And okay, let's proceed to the okay, so we have here the second problem. Now the first problem is actually uh, how you call this, the second problem is linear, or can be solved using okay, it's a linear DE. Okay, so linear ordinary differential equation, but there are some problems that cannot be solved using linear. For example, this one is here is a nonlinear problem. So when you say nonlinear, we cannot solve it using variable separable method. but instead we use here, instead of the LU decomposition, okay, when you say nonlinear, our matrix is nonlinear, meaning our variable to be determined is the second, third, or nth degree, um, nth degree, no? So here, if you notice in the linear, it's all on the first degree variables, but in the nonlinear you have more than first, and then so you have the boundary, no? So y of 0, then y of 2 minus 1. So we go very simple. So at x is equal to 0, y is equal to 0, and at x is equal to 2, then y is equal to 1. Okay, so those are the boundaries. So you can draw that one. Okay, you're in the drawing. At x is equal to 0, y is equal to 0. So I made a mistake. So 0, and then at 2, yeah, 1. So therefore here, so assuming the curve looks like this. Okay, so um, actually I don't know the curve, no, so I cannot express the y double prime equals negative 3y y prime. Okay, and so what we're going to do is to use the okay, use the we call it the Newton-Raphson method, okay, for the nonlinear expression. So here we have the function, so we define the function, which is this one, okay, 3y y prime. Okay, so if you call this function f, then you will use this function. So if you have other differential equation, okay, so you transform that one. So if you have y to the n differential equation, so this is f x y y prime y double prime, okay, sorry, okay, and then up to y to the n minus 1. Okay, so that is how but in this example we only solve for the second order differential equation, which is this one. Okay, and then start solution, and so these are just um, the here, okay, 0.5x1. So we will see later, no? So the residual is actually, since we cannot solve it linearly or linear programming, we solve it using nonlinear. So our goal here, we solve using the Newton-Raphson. So recall this expression here. Okay, so we use the r and p zeros, and then the first one is alpha. So um, because all of them are, if you can recall the finite element, so we will use this one and this one. Okay, so therefore we are using this one and this one here. So okay, so this expression here, this one here, and then this one here. So going to this residual, so you have minus 1, because our uh, at at sorry at actually this can be from here. Okay, this is from these two equation. Okay, so uh, y0 is equal to 0, right? So the residual is actually y of 0 minus 0, which is actually y of 0. So that's why here r is equal to y of 0. And for the other one, y of 2 is equal to 1. So the residual is actually yeah, this is y of 2 minus 1. Okay, so you just transpose this one, and the residual should be approaching to 0. Okay, So the residual should be approaching to 0 because it's like the error of the problem, no? It approaches 0. Okay, and so the same here, it should be approaching 0. So the numerical method here for nonlinear problem use Newton-Raphson. Okay, we will use the convergence or the gradient descent. Okay, so later on we will have, in the more advanced topic, we will talk about it, no, in machine learning, for example. But it's good enough to understand that our goal is to it's like um, solving using the, you can recall the Newton-Raphson in module number 3, if I'm not mistaken. We use the Jacobian, and we get the solution by using the Jacobian, so the first order, diba? Differential equation. It's like if you have a problem like this, if you have a solution space, so the Newton-Raphson is finding this is the optimum solution. If you are initially here, so the Newton-Raphson will go to this point, go to this point, go to this point until it reaches that one. So it it make use of it makes use of the how you call it, the iteration process. Okay, so and this the direction of this point, how come it reaches this point, is based on the slope, no, slope at this point. The slope of that point is going that one, no, and then at this point, that is the slope. This point, that is the slope. So basically that's the y prime. So that's the rule of the Jacobian until it reaches this point, which is, okay, the y prime here, or the slope is equal to 0. Slope is equal to 0. Okay, so that's the idea, equals to 0. So that's the idea of the Newton-Raphson. If you're not familiar with the Newton-Raphson, so I invite you to watch again the module number 3. Okay, so more of that. So we now go back to the original problem. So as I said, to minimize the residual, no? So we use the Newton-Raphson given the function and the x, and the tolerance or the threshold value. Then we also use the Gauss pivot for the some of the function inside the Newton-Raphson. Then also some of the swap rows. Okay, you go back to module number 2 or 3 to know more about this. And then we're ready for calculation. So our goal is to solve the function, okay, from 0 to 2. Again, this comes from this value here, this one. Okay, so from 0 to 2, your x, your the boundary, okay, and then our m is equal to 10, and then you have the h, and then you have the residual value here, the function residual. Okay, and you have also the start solution going to the to the previous one, and start solution x. So actually this is to iterate, no, so from the start, so you have the y values here, and so it returns the value of your y given the x. Okay, given x. So it's just simply the notation. Okay, and yep. So here um, I say we print to you the result from 0 to 2, which is correct, no? From 0 to 2, the answer should be 0 and 1. Okay, so which is correct, no? And 0 to 2, which is 1. So the numerical value is 1, which is the given boundary at x is equal to 2. So then we can conclude that our numerical method here is accurate. Okay, and okay, so yep, based on your boundaries. So this is not the same as the previous example, which is we we solve using the matrix, no, using the LU decomposition. Here we solve it using the Newton-Raphson. Okay, so if you we express this, the method in Newton-Raphson is not the same as the one in the linear, which is this one. We find the solution based on the first degree expression. Okay, and I think that's it, no? So this is we gave you the two problem solving examples. The first one is linear and the second one is nonlinear. As I said, the second order differential equation is the easiest example for the 2-point boundary problems. If you have more than 1,000 of order differential equations, which is in the multi-physics, no, problems, for example, if you have a simulation, okay, so you are going to make use of more efficient method. Finite difference method is the most basic. There are more advanced methods, and you might wonder how does Wolfram Alpha. Okay, so some of the computer. Okay, so you have Wolfram Alpha, for example. Wolfram Alpha. So how do you solve this? Some of the problem, for example, we can actually solve. We can actually try to solve this problem, no, using some of the computers. Actually, they're using numerical methods, and okay, so we can actually, let's see if they can solve this problem. Okay, and okay, so you have the second order. So this is the analytical solution. Okay, and this is very exciting, you know, how they were able to generate this one. This is more advanced way of doing more advanced way of solving a differential equation. So this is the solution, but you can see that um, anyway. So uh, this is very interesting, no? So this is another topic wherein your result, your answer should be in analytical solution. Okay, but they were able to numerically solve the 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 example, the equation, okay, based on numerical methods, no. The result is a analytical method. You can actually show the step-by-step solution, and but okay, we need to pay. Okay, so you can also do that. That's one of the advantages. So what is the importance of this one? Having known this, now this is true to any x. Okay, this is true to any x. Our problem here in this example, we are given with boundary. So what if it's unbounded? Okay, so the solution here is unbounded. Okay, because at any x you can solve for the value of your y. Okay, but our solution here is only limited with the 2, with the boundary. And anyway, so most of our engineering problems, we have boundaries. Okay, only in basic sciences, like those who were studying astronomy or astrophysics or any physics, no, something like they express their systems into equations. Okay, so they need the more general analytical solution, which is this one. Okay, so yep, so that's the difference. And our calculator, our for example, MATLAB, so we have the similar way of solving, but because of the advancement of algorithms, so some of the algorithms are more efficient. For example, they're not using the Newton-Raphson. Instead, they use a more efficient way of solving nonlinear um, equations. And for the linear, they are also more advanced, especially if you have 1,000 by 1,000 m by m, when your m is 1,000. So you have a sparse matrix, and some of the algorithms are very slow. So they need a more powerful computer. So in this case, we are using some of the algorithms they use more advanced. Okay, so that's end our module number 8, which is one of the one of the important thing we should learn for numerical methods. And you can observe that we use different um, techniques from the previous module. So if you are new in this lecture, so if you are just into this at this first video, I invite you to watch the previous modules. Okay, so I think that's it. Thank you so much for watching, and if you can make some comments or whatever, so please you can comment, and we can change, or we can try to improve our solutions. Okay, so thank you so much.